In this first class of Chapter 7 of the course of Basic Geometry, the following topics are presented: definitions about ellipse curve, eccentricity of ellipse, construction of ellipse, tangent to point of ellipse, inner and outer concentric circles, length latus rectum, circles director of ellipse, other definition for the ellipse. In this first slide of this first class of Chapter 7 of this course of Basic Geometry, it's presented a figure which shows the conical curves, ellipse, parabola, and parabola. The curves of the group called the conical curves, as it is generated by intersection of a solid called the cone, with inclined the plane relative to the base of the cone with an angle of less, equal, or greater than the value of the angle of generatrix of the side of the cone, also relative to the base of the cone. The angle of inclination may be less, equal, or greater than the angle of inclination of the generatrix of the side of the cone relative to the plane of the base of the cone. The figure shows the three curves, ellipse, parabola, and parabola. If the plane that realizes intersection is parallel to the plane of the base of the cone, the curve will be a circumference. In this second slide of the first class of the Chapter 7 of this course of Basic Geometry is presented the figure of the curve of the ellipse that will be the first curve of the set of conic curves to be studied. The conic curves are curves generated by the cut of a cone that is a solid by inclining the plane with respect to the base of the cone. According to the inclination of the plane with respect to the base of the cone, different types of curves are generated: ellipse, parabola, or parabola. The ellipse conic curve is generated by intersection of the cone trunk with a plane having an inclination with respect to the base of the cone itself, with an angle smaller than the angle of the generatrix line with respect to the same base of the cone. The ellipse is a curve symmetrical with respect to the two axes, called the major axis and minor axis of the ellipse, but it has different dimensions in the two axes. The ellipse curve is defined as the locus of points in a plane whose sum of the distance at the 2 points in the plane is constant. These two fixed points in the plane are on the major axis, and they are called the foci of the ellipse f1 and f2. The distance between the two fixed points is called the focal length and is represented by the letter f. The center point between the two foci of the ellipse is called the center of the ellipse, represented by the letter O. This slide presents the main elements and properties of the ellipse. Figure 7.1 shows the main elements of the ellipse without showing the drawn curve. The radius vectors of ellipse are called the line segments that join a point of the curve to each of the focal points. The sum of the dimension of the two radius vectors of a point to the curve to each one of the foci of the ellipse is constant, being this constant called the constant of definition of ellipse, and is represented by the letter C. The line segment connecting the two focal points of the ellipse is called the major axis of the ellipse. The center of the ellipse is at the center of the line segment joining the two focal points f1 and f2. Perpendicular to the main axis and passing through the center of the ellipse, it was drawn a perpendicular, that is the minor axis of the ellipse. The two ends of the minor axis are points of the curve, that is, they are points that have the sum of the dimension of the vector radius with value equal to the constant of definition of ellipse C. In this slide, the main elements of the ellipse are still present. The figure 7.1 is represented. Also, on the major axis, the points M and N are the ends of this line segment. The points M and N are also points of the curve, and the sum of the dimension of the radius vectors have the value of the constant of the definition of the ellipse curve. By joining with a straight line any two points of the curve so that this line segment passes through the center of the ellipse, this straight line is called the ellipse diameter. An example is the PQ line segment shown in figure 7.1. Join with a line segment and 2 points on the curve. This straight line is called the ellipse chord. The major axis is the greater diameter of the ellipse, and the minor axis is the smaller diameter of the ellipse. The four extreme points of a major and minor axis of the ellipse are called the vertices of ellipse, called the points M, N, C, and D. This slide presents the element called eccentricity of the ellipse. The figure 7.1 is represented. The division between the value of the focus distance f and the value of the constant of the definition of the ellipse c is a number less than 1, and is called the eccentricity of the ellipse, represented by the letter E. If the value of the eccentricity is 0, we will have a circumference with the two focus in the center of the circumference. This slide shows the methods of constructing the ellipse curve. To construct the curve of the ellipse, the two axes, the major axis and the minor axis, are drawn. In the major axis, the two focal points F1 and F2 and the two vertices M and N are marked. To determine the points of the curve, it is marked a point P between the two focal points F1 and F2. Centered on F1 and F2, circles are drawn with a radius equal to the size of the line segments PM and PN. Since the sum of the dimension of the segments PM and PN are equal to the constant of definition of the ellipse C, the sum of the radius vectors will also be equal to the definition constant C. Thus, the point defined by the intersection of the circles will have the sum of the radius vectors equal to the definition constant C. Thus, in figure 7.2, 2 points P and Q were selected and their respective circumferences were drawn according to the explained above. 8 points of the curve are generated. Using the 8 points generated by the points P and Q plus the 4 vertices M, N, J, and H, we will have a total of 12 points to generate the curve. In this slide, a tangent to a point of the ellipse is shown. The figure 7.3 shows an ellipse curve with foci F1 and F2, center O, and vertices M and N. It's marked in the curve the point E that belongs to the curve. From the point E are drawn the line segments EF1 and EF2, which are the radius vectors of point E. The bisector of the angle formed by the two vector radii is drawn. Drawing a perpendicular to the bisector by the point E, this straight line is the tangent to the curve at the point E of the curve. This slide shows the definition of the inner and outer concentric circles of the ellipse. The figure 7.4 presents the two circles, inner and outer concentric circles. They have the center at the ellipse center and a radius equal to the half of the dimension of the major axis and half of the minor axis. In the two foci of ellipse coincide with the ellipse center, we will have a circumference, and the inner and outer concentric circle will coincide with the circumference curve. The inner and outer concentric circles are also called the major and minor auxiliary circles of ellipse. This slide presents the definition of the line segment called the Latus rectum. If at one of the focal points of ellipse a perpendicular to the major axis is constructed, said perpendicular will intercept the ellipse curve at 2 points, K and L. The dimension of the line segment KL is called Latus rectum. In the figure, the formulas for calculating the dimension of this line segment are presented, using the values of the dimensions of the focal distance f and the definition constant of the curve C. This slide presents the definition of the director circles of ellipse. The two circles centered on the two ellipse fossae and radius equal to the constant definition of ellipse are called director circles of ellipse. This last slide of this first class in Chapter 7 shows some additional definitions about conic curve ellipse. The first definition says that any point that is within the curve, belongs to the curve, or is outside of the curve, has the sum of radial vectors at the point less, equal, or greater than the constant of definition of ellipse. The second definition states that any 2 points of the ellipse are symmetrical with respect to each other if the line segment connecting these 2 points pass through the center of the ellipse. The third definition says that by analyzing the ellipse curve, we conclude that the ellipse is a convex curve. Any straight line segment that doesn't cross more than 2 points on the curve